that leads perfectly into the distributed control systems here.
Yes.
Because it is literally just my vision of like how the distributed control should work in the future. Oh,
We should do it.
It's exactly my vision. So my vision of how distributed control should work in the future. Right to the camera. So if you have most of these machines, right? You want like an outward-facing Linux computer typically that's doing the coordination. It's doing your top-level sort of command. You want to provide some interface for people, maybe like a REST API. You want to talk to the rest of the factory, whatever it is.
Sure.
Typically, you want an RJ45 upstream, some USB ports, and maybe even a screen. Now, Raspberry Pi is absolutely perfect for that. But then downstream, you want real-time control. Now, have you ever worked with real-time Linux?
No, I have not.
So real-time Linux, there's a few sort of flavors of it. The most common that I've seen with like Linux CNC, for example, is you get a real-time patched kernel. And what they do here is everywhere that the kernel would interrupt somewhere and a few other little niche corner cases of things that weren't timing constrained previously, they sort of inject over the top of it with various patches, and I think it's actually entirely Git patches. I'm not 100% sure about that. And
Geez. Huh.
it's kind of wild. And I believe the Linux project has been trying to integrate that a little bit better and provide them better hooks to do that in the modern times. But early on, it was literally a patch that you applied that would remove basically all the non-timing, all the non-deterministic timing from the Linux kernel, and you could run a machine with it. And you could generate, for example, like the pulses for stepper motors with Linux.
Yeah.
Now, kind of bonkers, right? Kind of bonkers. I think perhaps maybe a little too bonkers for my taste sometimes. Because if you've also got something in user space going on, like, is there a better way to separate this? And this is really the question of distributed systems and distributed control systems as well.
So what's the main appeal? It's interesting because we were just talking about like PIO, and that's like almost like kind of a separate processing unit.
Yep.
So it's like, do you need real-time Linux if you have these PIOs?
Exactly. So, you know, the PIO concept and the sort of like mini and maxi CPU has obviously become prolific in phones for power applications, but you can also do the same thing with a single chip, like the TI Satara, for example, will integrate it's an ARM core, it's like an A7 or something like that, as well as a sort of mini CPU in the same package, right beside it to do precisely that.
Oh, interesting.
And they have some shared RAM. And so that's how you communicate between them. That's what the BeagleBone boards are based on, actually. So you can do some really cool real-time stuff with those.
BeagleBone, an interesting alternate universe of the Raspberry Pi.
Indeed.
Yeah.
I think they didn't end up going quite the same way because they were too expensive for a lot of the general purpose applications. And the real-timey stuff was a little too hard to access for it to be valuable to a whole bunch of the makers who wanted it for their CNC machine,
occupied kind of the weird middle zone. And they never released a chip. Obviously, Raspberry Pi kind of went deeper than I think anyone thought they would go at the time, I want to say. I didn't expect it.
I mean, like, particularly with the amount of aggressive competition, they've fared so well. They're still so prolific.
Yeah,
despite everyone nipping at their heels, you know?
Yep. But so the I mean, I guess I'm still a little confused. So with this mini CPU concept, is that one a real-time Linux? Or like, how does real-time Linux fit into this new world where you do have, like, you can tell another processor to go do things in parallel?
Well, see, that's the pitch, right? So the beauty of a distributed control system is that you no longer need something like real-time Linux unless you, for some reason, really need to centralize all of your
I see what you're saying. It is, okay. I wasn't thinking of a distributed control system as being like all on the same board, but no, it can be. You have a couple processors, PIOs acting kind of with their specific function, and you have a distributed system.
Yeah, it's kind of a tiering list, right? So my dream, my ideal sort of machine setup is that you have something like a Raspberry Pi or a Raspberry Pi compute module that's sort of calling the shots. It's providing the interface to the user. Then tiered down from that, and this is how they typically architect the lower cost ones today, is you have something like, you have a separate microcontroller, argument's sake, say an RP2350,
Sure.
that is basically doing all of your real-time control on the board. It's sending the pulses to the stepper motor drivers, controlling perhaps any servos if you have them, coordinating all those, and I don't know, you open the door and the GPIO for the door opens. It's the one that's sending that signal through. It doesn't actually need to go all the way through the control loop of Linux, which is fantastic. And what you see with things like Clipper. Are you familiar with the Clipper 3D printer controller?
No. So what is Clipper?
Clipper is a 3D printer control software where they have a Python application half and they have a C application half, or C++ perhaps. And it does exactly this. The Python overhead lives on a Linux machine somewhere embedded, typically a Raspberry Pi, because that's what everyone in this community uses, and an embedded microcontroller that does actually does the stepping. And they have a USB link between them typically. And so you can do all of your path planning, your motion planning, provide an awesome interface in the convenience and speed of a Linux machine.
That's pretty cool. Is USB, if it's on the same board though, isn't USB kind of like overkill?
How's your webcam attached in your computer?
I mean, that's true. So I guess there's some similarity there. But like, it can't like UART or SPI or whatever look like just a regular device? Or do USB devices actually look better? This is a little bit of a tangent. I guess this kind of relates to, in this distributed system, how does everything connect together?
It's really just a convenience of drivers, you know? And so if you have, everything has USB support, right? It is universal, as the name suggests. And so if you want that universal support and convenience for every possible, and you know, you're the firmware developer or the application developer for this, and you want to be able to support just about anyone to load this on any system, first-class USB support really goes a long way.
Gotcha. Okay. So, even for the same board. And I guess like, excuse me, I think USB also kind of has this advantage where I think you need a chip for it. That's a good question, actually. I don't know that much about USB, but USB can kind of be a hub, right?
USB can be. You need a hub.
You do need a hub
IC.
chip.
Yeah.
Okay.
Exactly.
So
it's not quite like CAN or I2C where you can just electrically connect them together.
Right.
It's not too far off it in the scheme of things.
Yeah. Okay. Very interesting.
So what you actually do from a controls perspective in these systems is your Linux machine does all the path planning, all that type of high level stuff, and then it'll send a buffer of, for argument's sake, 200 milliseconds of path, which is the kind of, it's above the maximum jitter that you're ever going to see in your Linux application. If you're trying to run a loop as quick as possible, you're not typically going to see higher than that.
So it doesn't matter that you don't have real-time Linux because you're just sending enough data where you're definitely going to be able to catch up.
Exactly. Enough like sort of path cache. If you know what you're going to do ahead of time, and then you articulate that plan to something that's able to just execute it. Aye, sir. Aye, Captain. No worries.
Yeah.
And I'm going to step at these intervals, which means that you have a nice, simple firmware application.
Yeah.
And you can do all of the harder things in a higher level language, which is really cool, both for development and also your ability to have more processing power at hand to do things like collision avoidance.
Okay. So now I'm starting to get what you're saying, where you kind of have, so kind of what you were recommending that the Raspberry Pi people do is they have both their like main Linux chip, like the really good one, and an RP20 2350 or 2040, because combining those two things together is actually very powerful. Exactly. You don't need to deal with real-time Linux and the various weirdnesses there, because you already have you have your real-time component on the 2040, and then your regular CPU, which is Linux, which is great and easy to use.
Everyone loves it. Yep.
Yeah, absolutely. I really like that. I'm always looking to have Linux on everything I do. So that is perfect for me. I'm like, always get confused in the low level land whenever I have to touch C. I'm like, this is not JavaScript. This is not Python.
It's not as convenient, or the important part is it's not as productive at the end of the day.
Right.
You can't do as much.
Right. Yeah. Something, I forgot to bring this up, but something this is really interesting. I guess it's slightly different than my model of the universe, because also the capabilities of microcontrollers in terms of processing power is getting really high, where it's almost like that main CPU is losing some of its usefulness. And like one of the things with the 2350 is it's got like, I guess, floating point number support and all this stuff for faster computation. So something I want to like. Do you feel like the computational requirements are going up? Like we need more to keep doing what we're doing, or like will these microcontrollers get fast enough where all of our requirements are met, or are the requirements kind of moving faster? Like, for example, if we all have edge AI running on our devices, then yeah, I don't think our microcontrollers are going to keep up. There's going to be like dedicated main CPUs all over the place for that kind of stuff.
Oh, okay. So the edge AI is a really particularly interesting one because I've seen people do bits and pieces with like, for argument's sake, an ESP32 where you have like a total of 500-ish flops. I think they've got do they have a floating point accelerator? Either way, you got 500 million operations a second, whatever that looks like in total between the two CPUs and how you distribute.
Wow, that is so much. Now that I think about it, that's hard to. I think about. I've been working on auto routing algorithms for like a week, and how slow they are in JavaScript. And then I'm like, I'm not doing that many operations. This doesn't seem quite fair.
No, that's why the beauty of compiled languages, you end up with a binary artifact that you execute.
Puts things into perspective. Anyway.
But I've seen, I think it was like a K260. It was like a $7 board out of some Chinese company that had a sort of like TPU-like accelerator to it, or for that matter, Google's TPU accelerators. They're just attached to a microprocessor, and you can do that edge AI type stuff.
Oh, huh.
Almost as a peripheral. Like you have a pretty typical microprocessor, whatever, it's a couple of 100 megahertz, has a tiny amount of RAM and flash. And then beside it, something that's kind of enormous that has no right being in a microcontroller, but it's pretty cool.
Oh my gosh, that is so cool. I know that I don't know if I can share this, but I got some insider information and some of the, not from a public company, just like, out of respect for startups. But with pretty high nanometer technology, you can get AI chips working. So there will probably be a lot of AI chips that actually do things. You know what I mean? That are actually meaningfully running transformers and LLMs and stuff like that.
Particularly as the models are getting better. It's insane what you can do with the smaller models as we've kind of learned how to make them more efficient.
Right. And the thing is even though NVIDIA is like, oh, we're built for AI, they're actually not that built for AI. They really have a lot of legacy stuff for gaming and stuff like that. And if you simplify to just what these transformer models do, you can use pretty high nanometer technology. I think we're going to see more chips for that. So a dedicated peripheral chip for AI definitely seems... But then there's got to be some standard for how to transfer that information. Is there anything like that? Like, I'm trying to imagine a chip you transfer text data to and get text out. It's such a weird...
Would you ever want it as a separate chip is really the question? Or would you always expect it to be paired with a microcontroller?
It's always built in there. Yeah, because the other way it goes is there's like an IP block that all the people, Raspberry Pi or whoever who's building a chip, just kind of puts in.
I think that's the more likely approach. Mainly because you at least need to ask your model reasonable questions and interface to the outside world. And as you say, like, you could slap a camera interface on there, I guess. That would actually be pretty cool and just like load a model in, but you'd need to program it anyway. And as soon as you're plugging a JTAG in there to program it at the factory, you kind of might as well just stick the
CPUs you might as well do the whole thing. Yeah, whenever you get a sufficiently highly priced chip, you might as well put like some like normal stuff on there and just pump out a CPU.
If RISC-V CPUs IP basically,
that's right,
free.
There's no cost. That's a really good point. Yeah, so we probably won't see a chip where you're like sending text over SPI. Like if you have a chip that's already that priced, you might as well just put more stuff on it so you can interface it easier or whatever.
Yeah,
very interesting.
Have you used some of the new Sonos?
The what now?
the new Sonos, not chips, the sound equipment.
No, not at all.
So they actually embed their assistant within the device, which is really
interesting.
Cool. So we're already starting to see this. Now, I'm sure they're running a Linux computer because they've got huge overheads and they're expensive devices, of course.
It's an LLM, like you talk to it, or is it for voice transcription? Or
I'm not sure what kind of models they're using, but they're assistant. I mean, it basically just does music stuff, but it does it all on device, which is really cool because the latency's super good.
Yeah, that's so critical. And Google Home and Alexa are so easy to beat right now. I think they're working on a lot of stuff, But yeah, you could, if you just are able to take one of the latest off the shelf LLMs and put it on board, you've beat them. It seems like really easy right now.
They're already winning.
Yeah.
So back to the more industrial application of
Right.
controls. Can you imagine when you start embedding these types of models at the edge in a factory, like the worker saying like, "Hey, robot, come on, don't stack them over there. Do a neater job or something like that."
Right.
Do you think we're going to bother complaining to robots, or are they going to become less deterministic?
It's a really good question. For that particular example too, like watching how Waymo drives, I almost wonder if like we won't be able to critique it by time it's there.
Yep.
Like by time it's there, it's so much better than us.
Yep.
That like, I guess I can still critique Waymo's driving.
I was going to say, it cut off a cement truck at a four-way stop today. So
yeah, I saw my Waymo do a circle around it, a four-way stop. Like it kind of like didn't know what to do because there was a bicyclist, and it kind of drove the outside of it. And I was like, this is crazy. Luckily, you've confused everyone else at the intersection, so nobody's hitting us. But
oh, you're in the car. You weren't waiting for it at the time.
Yeah, no, I was in the car. I was like, very interesting.
The specific application actually that's come to mind now, if you could embed this type of model at the edge with a microphone, is if someone's in a factory and they go, stop. Like that's actually pretty
that's
handy
huge.
to have. That's huge for safety.
Yeah, stop chip.
Yeah.
Those microphones though are really tricky. But yeah. What I want to see is more. Okay, so the hypothetical reality is chips that like, I don't know, maybe it's really tough because like it could be IP cores or it could just be built into CPUs or whatever. But like, I really want to see chips that just take camera data and like output text or something like that and do it in such a low power way. And then there's a ton of competition for that really low power method of doing that. And same with the stop command, right? Like voice, I imagine that's like a lot of cycles. It's something you could really optimize down to silicon, I think. So like it'd be really cool to just have super low power things that do that. Because today it's unimaginable to think I have a battery powered camera in a room, right? Because I think a lot of it, I'm not sure how much power a camera takes, but a lot of it does go to Wi-Fi transmission, like connecting and running the system that's able to compress it before it goes out and stuff like that. So I feel like dedicated chips for these kind of things could be big, but what we're seeing is more of a consolidation of hardware into a single chip, as you said. So
I have come across one company that does AI processing for hearing aids to figure out what you want to hear. Now, talk about low power applications.
Yeah.
That is a seriously low power application. And they, to my knowledge, actually got it working reasonably well. Now, they had to make custom silicon, of course. And the low power optimization there was imperative. Like they really had to go deep into it. But talking to one of their engineers, Davide, who now works at a company, Diode Computer.
Diode, yeah.
Yep. Also in the same space. Shout out to Diode.
Shout out to Diode. Great guys.
They optimized the daylights out of this to the point where you could fit it not only into that space, but that power budget. And with really good results for people who had hearing loss, because it kind of could, to some large degree, work out that you were trying to talk to someone across a table and that you wanted to filter their voice for all the others in the restaurant.
Wow. So this is already happening.
This is already happening.
Wow. That's crazy. Have you ever seen this tiny tape out stuff?
The tiny tape out? No,
yeah.
I've never come across that.
Tiny tape out is a program started by, I think, some people at Google. I could be wrong. And basically, they wanted to make it easier to make chips.
Yep.
And so every 6 months-ish.
Oh, okay.
Yeah.
The Google open source chip suite. Is that it?
So there's a Google open source chip suite, which this uses. But what they do is every 6 months, you're allowed to put your design onto a chip. And then they all, like, basically the chip is split into, 100 designs.
Oh, incredible.
And everybody gets a space. So for $150.
$150?
Yeah, it's crazy, right? You could get a space on this chip. I think the nanometer technology is pretty high that they use.
Of course. Who cares?
Yeah, no, who cares? And the other thing is they're really fighting. I think this is the biggest battle. Is they don't have access to the IP blocks that are essential. So they have to use these open IP blocks, and they're like slowly building up the thing. But it's clear it's going to take a while.
I'm going to have to check that out. Tiny tape out, $150. I'm going to be able to make my own custom silicon if I'm willing to wait 6 months.
Yep.
Now, that's 6 months at the moment. But you can imagine that as they accelerate that, they might, like theoretical future, you do one a week.
Yeah, as they get more interest. It kind of reminds me of back in the day, there was this place you could order purple PCBs from, Osh Park.
They still do it.
Yeah. So Osh Park, at the very beginning, I think you had to wait until the batch was done.
Oh, yes. I have heard
And it was
that.
like once a month.
It's still kind of slow. It's a couple of weeks. Still.
Oh, really? It's so slow. Okay. But yeah, they were basically waiting to fill a panel. It's really the same thing. It's kind of weird how similar chip design is to PCB design, and yet they are two completely distinct layers with their own tooling and everything.
Yeah,
so
and a different way of working for sure. It
really
branched off back in the 80s when you ended up needing to actually go down a different route. Like they were forced to go down a different route with IC design because there's just no way you could actually tenably do drag and drop.
Yeah, it's interesting too because it's it's a lot more programmatic, a lot more analysis done, design checking, like far more than PCB design.
You really want to check your design.
Because
if you do something stupid, like it's a really long cycle. I mean, 6 months for a tiny tape out, but even for a high-end chip manufacturer, you think that making a mask with precise features at the 4 nanometer kind of scale. And if you think about a mask for an IC as just an image, think about how big that image is. You have billions of components, but you're talking about billions of features on that nanometer scale.
Right.
And you're not just trying to describe where those edges are at a 4 nanometer resolution if you were to think of them as pixels. I'm actually not 100% sure how they're stored, but I anticipate they're vectors. You're talking about vectors with trillions of elements, right?
Yep.
And you need to actually raster that into a mask, into a mirror actually for those super high precision processes. This is an enormous file. Even transferring this to someone who could etch it, let alone the etching process, I imagine takes days.
Yeah.
Right?
Yeah.
And the processing, of course, on top of it as well to render it out. And so when you think that your development cycle is forcefully on the week scale as a best case, and I'm anticipating probably on a month for the higher end stuff, or on the months scale, you probably don't want to make a boo-boo.
Yeah, absolutely. Yeah, it's really interesting. It's PC board design kind of was like stuff you could always do by hand that kind of got so sophisticated that you could no longer do it by hand.
Yep.
And I guess that was like kind of the split or something. Wow, that's so interesting. Two different worlds. And maybe we'll have another split in some sense because
we certainly hope we do.
Oh yeah, absolutely. Yeah. And then what's the next thing? I guess plugging in things will be the thing you do by hand in the next iteration. If all custom boards are ordered fully assembled, the next stage of this is like people are like, I guess it's okay to plug things in, and then they'll get sick of that. They'll be like,
I want to delete harnessing.
Harnessing, okay.
Yeah, harnesses suck.
Like a testing harness,
or just even the harnesses in a car. So any cable, so because it's soft, so typically because people have to handle it almost always.
Yeah.
And there's some automation around it. Like you can get machines that will automatically strip and crimp the connectors on a piece of cable, for example.
Right.
But it's still typically up to a human to actually put that in the right slot at the back of the connector to feed it in manually. So we don't think about it much, but actually manufacturing these are soft goods. They're almost textiles in a lot of ways, right?
Yeah.
They're a pain in the ass to handle. They're a pain in the ass to automatically plug into anything. And they're still joined between everything that we make. And so, distributed control systems again, RJ45s, like RJ45 Ethernet cables are absolutely ubiquitous. And so if you can either fudge something onto those cables, and I've run CAN over them in the past, or you can run ISOSPI over them, but it's kind of annoying. I would much prefer to be running Ethernet, for example.
Yeah.
And that's what obviously a lot of automotive applications are doing these days. They're running Ethernet around cars.
Yeah. That's really cool too. Just like
not RJ45s to be clear, but
right. Yeah, it's really cool to think of like everything in your car kind of being like on a network that's really accessible from Linux or something like that.
Yep.
That's a really, really cool concept. It's so much easier for me to grok than like all these like SPI connections all over the place and, this kind of hierarchy of connections. Because I guess one of the benefits of that is like you don't need. I don't know how cars are designed, but I'm imagining you have like your main controller, and then you also have a lot of sub controllers which control like, I don't know, everything in the back of the car, everything in the taillight or something like that. I imagine they don't all wire in individually to the main controller. But with Ethernet, you might be able to pull something like that off where everything has, its own IP, ideally, but if we can
its own jurisdiction.
Its own jurisdiction, yeah.
No, that's exactly how cars are designed. And that was the sort of revolution in the 80s and 90s with CAN in the first place, is you could already do that to some degree.
Oh, okay. So currently with CAN buses, kind of everything is kind of a flat network.
It is a flat network. And actually, that's one of the exciting things that Linux supports socket CAN, right? Which is actually like quite a good CAN layer. It's really easy to interface with. The tools are great. And you can, with pretty decent support these days, add a CAN IC to the SPI bus on something like, again, a Raspberry Pi, for example. And that way you're providing your Linux machine with direct access to a flat CAN bus of distributed devices that can work to some large degree independently. And it's a fun question. It's such an important question of where do you put what control loop? One of the really fundamental questions of distributed control systems. And so, again, take the classic machine example, CNC machine, everyone can think of that, or a 3D printer. You got your top level, where should I go and how far should I go kind of computations done at the top level, Python, human interface, all that type of stuff. Today, typically instructions go to a single microcontroller via, as I mentioned, USB, or the likes. And then it will disseminate those via super time critical steps and directions out to individual stepper motors. But if you move the CAN layer sort of one layer higher from the microcontroller directly to your Linux computer, which is what automotive has already been doing for decades, right? You might now say, okay, well, a refrigerant loop, for example. I can't control the compressor speed and the valve position on my Linux computer. That would be insane.
Is that what it's called in a car, refrigerant loop for the cooling system? Is that right?
A subsection of the refrigeration, the HVAC system.
Okay,
you
gotcha.
have a refrigerant loop. Basically how this works is there's a compressor, which is just a motor with a compressor on it. It will take a refrigerant starting as a gas, compress it down. Now as a high pressure gas that's hot, you run it through a condenser that will dump a bunch of that heat out and turn it into a liquid. And then you basically bleed that liquid through a small valve, which is, again, controlled typically by
This is how all cooling units...
This is all cooling units ever.
Okay.
A small valve, which is... you typically have control over this valve. It's an EXV or variable expansion valve, basically, with a stepper motor that puts a pin in it, basically, to set how large that hole is. And the expansion of that gas, obviously, cools it down. You run it through an evaporator, which gives it a whole bunch of heat, obviously, and that increases the temperature back to a gas, and it goes back to the compressor.
Very interesting. Hey, when I never asked what firmware you worked on. Can you share what piece of that? Because I'm just realizing
that
now.
Firmware.
Okay, you were on the refrigerator. Because I was like, we're talking about all this. I'm like, yeah, there's a lot of systems in a car, isn't there?
There is.
They're all very important. Yep. You could probably have a team on each one.
You do, yeah. I was thermal controls firmware.
Oh, gotcha. Oh, okay. All right. Wow, that's super cool.
And so in this specific application, this is actually something really interesting that, we at Tesla, for example, looked at, is where do you put that refrigerant controller? Now, obviously, the low level, that pin valve, that EXV, needs to be super close to the device.
Right.
Not just there's a few considerations distributing your control system. One of them is sort of speed, your bandwidth.
Right.
Another, so how often you get an update. Another is travel lag. What's the latency between something occurring in the real world and you actually receiving that update?
Oh, interesting. You had to think about that a lot.
Absolutely.
I mean, this is probably pretty small too. Yeah. This difference. We're talking about probably a millisecond or less.
Specifically with the refrigerant systems, they're like fairly robust, and so you're talking on the scale like 10 to 100 milliseconds is acceptable, but you obviously want to get that pretty small.
Gotcha.
And then the final thing is safety. What happens if you cut that cable, something conks out, something bad happens anywhere on the car? Can you accept that going down or that losing control of that system?
Right.
Now, for refrigerant, the answer to the third is no, you can't. And the first two as well, it needs to be fairly fast and it needs to have low latency for those controls to work properly. And so you put a PID control in the microcontroller. And now that is typically super easy to do, right? Like a PID control. Are you familiar with a PID control?
Yeah. That's hold on, I'm gonna remember. One's derivative, one's integration, the
Proportional.
P proportion.
Yeah.
That's the easy one too.
It's the easy one. It's look, honestly, the winning control system out of most things is a PID. It's the most ubiquitous control scheme.
Yeah, it's like annoying because you try to be clever and then you put in a PID loop and you're like, all right, whatever.
Oh, damn, it actually works pretty well.
Turns out they figured this out 50 years ago, whatever.
Yep. And exactly. And they work fantastically. The one thing that they don't do super well is travel lag or latency. Because you end up winding up that integration term and really annoying it.
Oh, interesting.
So even if you increase the bandwidth, the speed of that control loop to infinity, you're still going to have the problem of the latency that ends up winding up your integrator and making it really hard to control.
Wow. Do you fix that? Yeah, and you fix this problem in software. So is there like a name of a PID loop that also takes into account latency in some way? I guess... Yeah, I never thought about this not being kind of handled automatically.
You can incorporate other control elements like feed forward, for example, to anticipate what should have occurred in the real world already.
Oh, interesting.
And offset that.
Okay.
So you change your sort of error feedback path a little bit and you can kind of compensate. But now we're complicating things and you need to know much more about your system.
Yeah.
So the ideal case in these distributed systems is if you need a PID controller, some closed loop control, get that as close to your devices as possible.
Yep.
Microcontrollers. Perfect to do that, easy to implement.
But is the wire transmission speed really the issue, or is it the CAN bus congestion?
CAN bus congestion.
I see.
And so this is the next thing is like, okay, so how quickly does the message get up there, and how do you send those messages?
Yeah.
So we send them periodically, typically on a CAN bus. And in all these robotic systems, periodically is typically the best way to do it because you don't really need to think too much about what priority things need to be, when you should need to send it otherwise, if it's worth sending something. You get acceptable compression. And so you can take 100 samples on the downstream, you can average those out. Perhaps you send 2 values, the mean, the mode, something like that.
Okay.
And then you end up with that data upstream. So this is the other thing about distributed systems, of course, is you typically have lower bandwidth between your nodes than you're going to have inside of them, of course.
Right.
And so you need to do some kind of compression. And the dumbest thing to do is do that in the time domain and sort of squash them down with a mean, average that out. And if we go back to this machine control, it's the same thing. Your stepper motor's exact pulsing. Now that's like bit banging a pulse on and off is hard. But if you say that I want you to go to a certain position, trivial. It's a single number. It might, perhaps you use a 16-bit or a 32-bit integer to indicate what position you want your stepper motor in, but fantastic compression, right, of course.
Yeah. Oh, that's so interesting. I'm imagining a bunch of Tesla people at a table, and they're all fighting over how much allocated bandwidth they get. Exactly. How much they need.
And you sort of keep going with this concept. The thing that was really interesting discussion I had, as a design discussion of the distributed system, is where should you put the control of your, like, what question should you ask of your microcontroller? You don't want to say, you don't necessarily obviously want to say the valve position. That's a bad one because you need to update it really quickly.
Right.
But perhaps and then there's other elements that need to be coordinated with that, as like your compressor, for example. But perhaps you do want to say how much heat you want to pump. Today, a lot of these controllers will take in a target like, what do you want the cabin temperature to be? Now you have really complicated firmware that needs to take into account a lot of this type of stuff right in the bottom device. But like this is the hard firmware. But if you draw that up and if you accept that your Linux system is part of your control loop, then all of a sudden you can have much more complex algorithms, not necessary for thermal controls, but for an industrial robot, for example, all the path planning, it kind of is.
Yeah.
But you can offset all the complicated stuff, and if you ask the right question to your servo drive, for example, or what position do you need to be in, if you give it a path instead of an explicit position, you can simplify your full firmware stack in a really interesting way.
Yeah, that is super interesting. So basically, as these processors get better on the edge, you can theoretically, I mean, there's a really interesting possibility here for new firmware that kind of like auto figures out how to distribute that or like makes it easier. Because you're not going to be able to get over. It's not just the CAN like protocol, right? It's the fact that you have a long line that a lot of things are connected to. You're not going to be able to send all the data.
No.
That's never going to be possible. So, yeah, I can't really think of a way to do it except having the logic closer to the nodes.
Yep.
Wow.
It's the fundamental question, right? It's like, where does your logic live?
Yeah. Wow, that's crazy. And this is all just data going on in a car. It's funny because we transmit like these huge videos all the time. We're like, oh yeah, there's like infinite room for data, but
we'll talk about distributed
really.
Systems, big data, like Netflix, right? Like
yeah,
they are big into their distributed systems.
Yeah, absolutely. Everybody thinks about distributed systems to some extent now, and there's a lot of new techniques. It's almost like I'm trying to draw parallels between like web techniques like serverless, where you kind of don't worry about the server, you worry about what logic is it doing, and then it's just automatically scaled, right? It's almost like I don't know. It's almost like just hypothetically, if you had this RP 2350 at your edge or RP 2040 at the edge, and you could program it from that main CPU, you could really just send it whatever programs to run. And on the fly in a car, that'd be really weird. But some version of that where you say, hey, I want you to run the PID loop with these parameters because we're in eco mode or something like that.
Yep.
That makes a lot of sense to me.
So actually, that's a really interesting one. If we go back to motor control there, for example, maybe you don't send the application, the full firmware, but say you have a robot arm. The response of a joint changes hugely depending on your position because the gravity acting on it or how much leverage you have at the base is completely dependent on what's happening upstream, for example.
Yeah.
So if you were to have a servo motor and you don't want to put the control loop on a real-time Linux machine, but you do want the Linux in the loop, right? What do you say? Well, okay, motor position and a path. Like what you're doing for the next 200 milliseconds makes sense.
Right.
But you might also want to send a map of like future PID constants so it can maintain a certain level of performance as all of those, everything from the mass moment of inertia to the damping changes as the arm's geometry changes.
Yeah. So basically, yeah. And then you're getting into the space of you're almost sending a full program. You're sending like the parameters of a program, essentially.
Exactly.
Of a long program, because arm position can go all over the place.
Yeah, exactly.
Whatever it needs. Wow. I mean, I agree with it. It makes a lot of sense to me that that's how kind of more complicated distributed systems will work. And I never really thought about that. You know, I always thought distributed systems were kind of a server thing, but no, definitely not.
They're
probably
all around us.
Yeah, they're all around us, and they actually seem a lot easier now for web servers. It's like you're not dealing with web servers. A lot of times they're homogeneous.
Okay.
But you're basically running on the same hardware all the time.
Yep.
And here you have to have different hardware because you need real time here, you don't need real time here, etc. And then you need like something in the middle.
And different peripherals, of course, as well.
Right.
Like, your RP 2040 has plenty of ADCs, for example, but I think the Raspberry Pi proper.
That's right.
Typically, I mean, I think it has one or two, but like not very good ones.
Yeah. And I think even with the RP 2040, people didn't love the ADC, so you might even, I don't know, have you used the ADC? It's probably fine.
I have not. No. I've always
I was looking at all the complaints about RP 2040. A lot of people were like, this.
Oh, on the RP 2040. Sorry, yes, I have.
Yeah. Oh, you have? Okay.
Yeah.
But you never had a problem with them, or they're okay?
I mean, they're not good ADCs in like microcontroller terms, and this also comes down to control loops and timing, right? So the 2350 has ADCs that can do 500 kilosamples a second, which is like getting up there. That's 500,000 samples a second. It's not too bad for something measured in the real world.
Right.
I can't remember what the exact rate of the 2040 is, but the problem with it is you couldn't necessarily time your ADC reads particularly well. And if you're doing something like motor control, for example, you need to measure the current that's running through the motor when the switch that's driving that motor is on, because otherwise you haven't got a leg in there to actually measure the current. You're just going to read zero.
Right.
And so good microcontroller ADCs will have, and PWMs will have means to configure interrupts to set when it actually needs to trigger that.
Yeah.
So if you're running some firmware like simple FOC, simple FOC, it only supports some processors because you actually need the hardware to exist, unless you're going to bit bang it, which isn't really tenable, but you need the hardware to exist to sort of trigger other parts of the peripheral to do its job too.
Yeah. That makes sense. Huh. Well, I can't wait to hear your impressions of the 2350.
Can't wait to play with it.
Yeah. It could be a little while, but yeah.
Thank you, Seve.
Yeah, let's
Fantastic talking to you again.
Good time. Yeah. Never know when exactly or how to end it, but